Hello everyone, this is Elon, and today I will present our work accepted into EMNLP 2021 as an oral presentation. And our work is about improving zero-shot translation by representation and gradient regularizations. So it's a joint work with Akiko, Alex, Prasar, Stephen, and Henny. This work was done when I was interning at Microsoft. Our work is on multilingual NMT models, where the de facto baseline model is simply adding the target language symbols in the source, and we could in this way train a multilingual NMT model to serve for all the translation directions. For example, we append in the source a special token to French, then the model are trained to generate to translate into French, so on and so forth for other languages. And although it's very simple, we also support so-called zero-shot translations. For example, performing French to German translation, even though it's only trained on French to English and English to German data. This has been the de facto standard for multilingual machine translation, and it works really well for many languages. However, despite the attractive property of multilingual NMT model that it could learn zero-shot translations, it often produces very low-quality translations, especially into a wrong target language. This is so-called off-target translations. Below, we show the off-target rates of our baseline model trained on two popular datasets. And we can see that the off-target translation is very common on even high-resource languages. Previous approaches addressing this issue often resort to back translation. However, leveraging back translation data for zero-shot directions has a few weaknesses. First, it usually hurts the English-centric performance. Then, the need for back translation data grows quadratically with the number of languages, so it's essentially not scalable. Third, it doesn't work well with extremely low-resource languages, since the generated back translation data are of very low quality. The intuition and motivation about our approach is that off-target translation is usually caused by the failure to model for different target languages and generate differentiable representation for them. For example, if those representations are not differentiable between different target languages, the model will essentially map them into the same token, so it will be off-target translation. We instead propose to address this issue by regularization on both representation level and gradient level. At the representation level, we enforce differentiable representations for different target languages. And on the gradient level, we align the training gradient for each language with the oracle gradients we capture during training. And the oracle, we use a dataset in our setup. For our proposed representation level regularization, we append language ID layers on top of the NMT decoder states and include its loss as an auxiliary loss during NMT training. So essentially, during training, we take the source as input and feed it through the NMT encoder and then NMT decoder, and from the decoder states, we have the standard NMT loss. And then we feed the decoder state into those language ID layers. In our paper, we implement language ID layers as a few encoder layers. So it's similar to like a few BERT layers. And from there, we predict the target language during training. And the classification loss is represented as the language ID loss. And during training, we add these two loss together. And our results show that it works pretty well. Meanwhile, we also propose a gradient level regularization. It's inspired by recent gradient alignment-based optimization method. We propose to regularize the training gradients by the gradient of a small amount of oracle data. In our setup, we use a dataset as oracle data. The intuition is that we have access to like thousands of dataset pairs, for example, 1,000 for WMT and 2,000 for OPUS data, so that we can apply PCGrad from Yu et al. 2020 to make sure that the training gradients are not conflicting with their dataset gradients for each target language. Here we introduce a brief preliminary on the PCGrad proposed by Yu et al. So the PCGrad is proposed to address the gradient conflicts between multitask learning laws, where the conflict is defined as negative inner product between their gradients. For example, in the below figure, in the figure A, the gradient I and gradient J are conflicting, and in the figure B, we project the gradient I into the normal plane of gradient J so that their dot product is 0, so they are not conflicting. Similarly, in graph C, we can project gradient J into the normal plane of gradient I. So the algorithm of PCGrad is essentially two for loops, and to enumerate all the task pairs of I and J, and whenever they observe a negative inner product, which is the conflict, we project gradient I into the normal plane of the gradient J. However, there's one significant drawback for this PCGrad approach, is that while we're doing this two for loop enumerating all the task pairs, there's no guarantee that after this two for loop, all the pairwise conflict will be resolved. And actually, most likely they are not. While in our proposed method, we only project the training gradient according to the oracle gradients in order to deconflict between the two. So essentially, every n step, we update the oracle gradients for each target language. And then for each step during training, we check if there's a negative inner product between the training gradient and the oracle gradients. If so, we project the training gradient to the normal plane of the oracle gradient to deconflict. So this slide is the experiment setup we have in our work. So our models are in transformer big, and we tokenize this dataset with sentence piece to form 64K vocabularies, and we train with big batch to simulate 128 GPUs, and each model is trained with 40K steps. So here's the dataset we use in our work. We borrowed WMT 10 from Wang et al. And OPUS 100 from Zhang et al. And noticeably, on OPUS 100, we found a significant overlapping between the dataset and test set. So we perform an additional step of deduplications, essentially deduplicate the training and dataset against the test set. For the evaluation on Oracle data setup on two datasets, on WMT10, we use the in-house multi-way evaluation dataset generated from WMT19 testset, which include 1000 for dev and 1000 for test. We group all the available datasets by the target language and concatenate them separately to form our Oracle data for each target language. And we further split the Oracle data by 80-20 and hold out the random 20% only for checkpoint selection. And on OPUS 100, we additionally sampled 2000 zero-shot dataset to match the 2000 test set using the official OPUS scripts. And for speed up, only on the OPUS 100 dataset, because there's 100 languages, we merge the language that only consists of English-centric datasets. Actually, most languages only have English-centric datasets. Since our target gradient projection method, i.e. gradient level regularization method, TGP, rely a lot on the zero-shot dataset in the Oracle data, so we further ablate the zero-shot dataset usage in the Oracle data for all the evaluated pairs. So below are the statistics of our Oracle data on both WMT and OPUS. Noticeably, for this ablation study, we only remove the Oracle data for the evaluated pairs. So in our experiment, since there are n squared translation pairs, we only evaluate 12 pairs. So we remove those Oracle data while keeping the rest. Here we can see some interesting learning curve plots from the TGP method. So the TGP will start training from the 40K checkpoint from the baseline model, and then did an additional 10,000 step of TGP training. So for this 10,000 steps, we see that compared to the baseline model that see a gradual decrease of the training loss, you actually see somewhat a gradual increase for the training loss. We hypothesize that this is acting as a regularizer to prevent the model from overfitting to the training set. And on the other hand, for both English free and English centric BLEU, we see a significant increase on both. So this definitely demonstrates the effectiveness of our TGP method. Here is a detailed English-centric result on WMT data. So on the top we have English to everything else, and bottom others to English. And for each system, the bilingual denotes the bilingual model trained on each separate language pairs. And the baseline is what we have for the multilingual NMT model. And the fine-tune is when we fine-tune the model, additional 10 steps on the oracle data we captured. So this is acting as a comparison to the TGP method. And for our method, there are two setups. On the top, we have the normal TLP and TGP, and on the bottom, we have the TGP star, which denotes the TGP training in the zero-shot manner for all the evaluated English free pairs. In a nutshell, the TLP method gains 0.4 BLEU and 0.3 BLEU on one-to-many and many-to-one scenario, while TGP gains more than 1 BLEU on both scenarios. And together, TLP plus TGP perform better than TGP alone in the zero-shot settings, while perform similarly on the normal settings. Here are the interesting English free results on WMT10. In a nutshell, TLP gains more than 2 BLEU points and TGP gains more than 5 BLEU points, averaging across all the translation pairs. And they can both do significant amount of off-target translation reductions. So thank you everyone, and for more details, check our paper. We also released the code and rebuilt, i.e. deduplicated OPUS data available on the GitHub.